Good day, everyone. My name is Rutvik Shah, and this is my CS 499 Honors Seminar presentation for the topic of Artificial Intelligence in the Automobile Industry. This presentation aims to explain what autonomous vehicles are and the science that goes behind it for its system development. We will talk about the hardware that goes into it, along with how the software utilizes the data acquired from it to act on it, making it seem to have its very own brain that makes sound, human like decisions while driving. We then move ahead to the computing side of it by diving into artificial intelligence. We will cover the fundamentals of AI, machine learning, and deep learning, while talking briefly about advanced mechanisms that are used today for automation projects. Once we have a grasp of this, we connect the dots to producing an autonomous vehicle. Lastly, we must discuss liability concerns and other gray areas to look for that ultimately pave the path towards future development of this industry. Sounds good? All right, let us move ahead. Firstly, the basics. What exactly are autonomous vehicles? We can define an autonomous vehicle as one that senses its environment and makes sound decisions based on it without the need of human intervention. The Society of Automotive Engineers has laid out an in depth explanation of the stages of automation for driving. If you look at the picture, there are a total of 6 stages numbered from 0 to 5. Stage 0, as its numbering suggests, this level has no automation and the driver performs every task. Stage 1, a step ahead of its predecessor, this stage has a single automated system. An example is to have cruise control, lane control, and more. Stage 2. This is what we see in most cars today. The vehicle can partially drive itself. It can perform actions like steering, acceleration, etc. But the driver still monitors everything and can take control anytime. Stage 3. Automobile companies like Tesla are developing cars that work on this stage. The car can detect the environment and can drive itself for most part. The driver can still override and take control at any moment. Stage 4. Vehicles in this stage perform all tasks without human need in a limited geofenced area. Google Waymo is one such example of this stage. Stage 5. This is it. This is the peak of automation with vehicle able to perform every task. There are no limitations and no need for the driver to take control of the car at any given time. Why are autonomous vehicles gaining popularity? The answer to this is amazingly simple. Think about the problems with current traffic managements. To name a few, we can achieve transportation efficiency. We optimize less parking space since cars would not need to be parked. People unable to drive can still travel in their cars without relying on others. There would be diminishing injuries and accidents due to human errors. We could eliminate problems like distracted driving, driving under influence, and more, which cause a tremendous amount of accidents every year. Another reason could be envisioning the future luxury. Vehicle manufacturers can focus on developing luxury for passengers, which allows them to gain a different marketing edge. This explains why companies like Tesla, Google Waymo, Apple, Bosch, Mercedes, Audi, and more are racing to launch the next AI powered breakthrough commercial vehicle out in the industry. Now that we have a basic grasp of autonomous vehicles, we can move forward to understand the science that goes into making such vehicles a reality. Before we move further, there is a simple elementary formula of developing a product. A product is nothing but the combination of hardware and software it uses. The case with autonomous cars is no different. Now, if we talk about the hardware, to develop a vehicle that can sense its environment and make decisions as quick as possible, we need a certain range of accessories. To list a few, a fast and reliable processing unit that is capable to efficiently perform real-time computations and calculations. We need multiple cameras covering every angle and blind spots of the car. We need GPS systems for real-time feed of traffic flow and location. We need radar systems to detect objects nearby. We need LiDAR systems to generate 3D vision of the vehicle and its surrounding. Odometry and inertial measurement units are always a welcome addition. Moving on to the software, there is a common loop structure usually followed while designing softwares. It can be roughly explained in the following steps. The system takes the data accumulated from various hardware components as input. The system then analyzes, processes, and compares the data for matches in its database, which is possibly linked to the cloud. Based on possible matches, the system then decides to execute a certain instruction set, and once ready, it is sent to the output feed to be executed. It is important to note that the system is always ready to execute and prioritize emergency protocols and override conditions above everything else. The system loops back to repeat this process infinitely many times. With basic software implementation laid out, we can move ahead to learn about how these decisions are made by the system. What we want to understand is how the system makes decisions on its own without human intervention. It is like the system is mimicking human behavior. This precisely is termed as artificial intelligence. There are countless AI algorithms like heuristic searches, statistical analysis, and more. But the ones we are interested in for the scope of this presentation are machine learning and deep learning. What is machine learning? Exactly what its name suggests. It is a machine that learns to perform tasks by itself without being programmed explicitly to do so. Now, machine learning can be broadly divided into three main categories. This can be seen in the picture on the right. We have supervised learning, unsupervised learning, and reinforcement learning. Number one, supervised learning. As suggested by its name, this is a training environment where we consider ourselves to be more knowledgeable than the system, thus acting as superiors and directing feedback to the system. Common examples are regressions, decision tree algorithms, etc. Number two, unsupervised learning. This is quite opposite to supervised learning. There is no known output, no known data set to work with. There is no feedback provided to the system. It must learn everything on its own. Common examples are clustering of data, association rules for systems, etc. Reinforcement learning. This machine learning type can be better explained with the use of an example. Think of a scenario where you are training a pet dog. You can train the dog by rewarding it with treats for every correct behavior exhibited and not doing anything for incorrect behaviors. Soon enough, the dog will learn that good behaviors are what gets it treats. So it will listen to the commands and do the exact trick it was trained to do so. This is called positive reinforcement. Similarly, if you lightly hit the dog on its nose every time it does something wrong and not do anything when it does something right, it will learn to not do certain things that end up with it being hurt. This is called negative reinforcement. We use this same ideology to train software systems as well. Now that we have a clear understanding of machine learning, we can address a few algorithms in use today for automation purposes. Number one, SIFT. Scale invariant key points are extracted and stored from an image. In this algorithm, every new image is then compared with it to identify objects. This is helpful to identify objects hidden behind others that are only partially visible. Take an example of a car hidden behind a tree. SIFT would be able to guess that the object is a car seamlessly. Number two, ADA boost. This algorithm develops on the idea that if standalone algorithms perform poorly, a combination of those would be more efficient in performance. For example, if algorithm A computes a result in 1 second and algorithm B computes the same result in 2 seconds, then a combination of algorithm A and B is likely to compute the result in less than 1 second. Number 3. Text on Boost. It has a similar base as ADA Boost, but Text on Boost is used mainly for image classifications. This is useful for our specific cause of autonomous vehicles. An example is that Text on Boost learns that pixels under the category of horses usually go along with pixels under the categories of farm, grass, stable, and other related things. Number 4. Histogram of oriented gradients, or HOG. This is one of the most basic applications of machine learning algorithms. What is of note is that HOG performs exceptionally well in detecting human figures. HOG achieves this by analyzing how the image intensity changes, which creates a gradient history that ultimately helps in classifying objects, especially human-like figures. Number 5. You only look once. YOLO is an alternative for HOG. This analyzes the image as a whole and then divides it into segments which are matched with the previously analyzed whole image to distinguish objects, people, and more. By contrast, this is faster than other algorithms because you only look through the image one time. Another example of machine learning is the deep learning method. Deep learning is so important that we need to explain it as a separate entity. We can say that deep learning is a subset of machine learning where the system is envisioned as having a neural network-like structure. It is the closest representation of our brains and its neurons. We can consider the deep learning algorithm to be a statistical method that extracts various features and attributes from raw data sets provided to it. To get a perspective of this method, let us go to the very basics, the perceptron learning algorithm. Perceptron learning is based on the operation of one single neuron. This artificial neuron is comprised of five main components. It has various input nodes labeled here as x1, x2, and x3. These input nodes are each connected to what we call the core of the neuron. Each connection has a certain amount of weight associated to it, labeled here as W1, W2, and W3. Inside the core, we calculate the weighted sum of all inputs. If the weighted sum is greater than a certain threshold value, we fire up a neuron just like a real brain neuron would and transfer the data to the output node labeled as Y. Now that we understand the mechanism of a single neuron, let us envision a whole layer of neurons and then layers of those layers, all interconnected. This interconnected system would be called a neural network. For our benefit, let us apply the perceptron concept on a wider scale. Let us assume a neural network to process and classify images. Assuming that we have an image of a dog here, we feed it as raw numerical pixel data to our network via the input nodes. The network then breaks it down to the core and starts comparing the pixel data with its database. Every match would fire up a neuron. There would be countless links of neurons between every layer. All of this happens amongst the hidden layers. Once the computation is done, we would come out at the output nodes with a classification that may denote the image as roughly 80% dog, 10% cat, 8% horse, and 2% mug, for instance. Since the majority of the image lies in 80% dog, we store the image under the label of dog. And this is how we process an image using neural networks. What we just described is a simple high-level neural network. There are other advanced high-level algorithms of deep learning that implement neural networks. Some of them are convolutional neural networks or CNN. It specializes in image or video processing and is remarkably similar to the network we just described. CNN is an algorithm of importance for developing autonomous vehicles. Recurrent neural networks. These networks work in recursive layers and are thus considered a good choice of algorithm for recognizing speech patterns, other types of pattern recognitions, and handwriting recognition. Generative adversarial networks. These are networks which we not only allow the system to learn, but we allow the system to create. A very famous application of this network is what we see in the deep fake technology. With this, we conclude our study of computational algorithms concerning the software side development of autonomous vehicles. Now, we can successfully identify how everything comes together to form an operating autonomous vehicle. As the image shows, component 1 is our hardware side of the vehicle. We use technologies like LiDAR, radar, cameras, and more to provide input to our component 2, the software. Once we have necessary input, we can make use of various machine and deep learning technologies discussed to make decisions and judgments. Once we decide on a course of action, we feed it through output to component 3, which in turn performs functions like automated driving, lane changing, braking, object detection, voice recognition, monitoring driver behavior, and much more. The action data, which is a byproduct, is sent back to our software, which is used for our cloud based memory to form new or improvise existing rules if the need arises. It can also be used to customize experience and store details unique to the driver. This allows for changes to happen instantaneously over the air to the whole fleet of vehicles. Now that we successfully understand the fundamentals of autonomous vehicle design, we can discuss about certain topics that must not be left out. These discussions are an integral part of an individual working in or learning this field. This is perhaps the most important thing and is what paves a path forward for the future of this industry. We need to discuss liability concerns and other gray areas to look for while building this technology. There are two major concerns. Number one, accident liability. This requires that we ask ourselves as developers important questions like who is liable in times of accidents? Would it be the manufacturer, the developer, or the vehicle owner? How do we fairly assess situations like these and come to a just and ethical decision? Number two, is the artificial intelligence of our system on par with human emotional intelligence mechanisms? We know that as drivers, we exhibit various non-verbal gestures, emotional cues, and other subtle hints to and from fellow humans that allow for seamless judgment calls and prevent countless accidents. Is this scenario replicable with our AI? Can the system register those cues and hints that seem so minuscule but end up having life saving impacts in a matter of seconds that only humans can understand? With this, we have planted the idea of the two most vital ethical dilemmas. We can now discuss some other conditions that need solutions. How about operating the car in extreme weather conditions? How about when the car loses network connection? Can it safely drive? And if not, stop and assist the humans inside? How about when the software of the car gets hacked? Can we assure the safety of our passengers in situations like those? Who is liable if something goes wrong? How about managing hardware malfunctions, software failures, etc.? Are there good procedures in cases like these that can guarantee passenger safety? Is the current technological state enough? Think about areas in the world that have little to no network. Think about routes that are not yet available on mapping technologies. Think about the processing speeds available to us now. Can we achieve everything just yet? The day we find an answer to the questions outlined would be the day that we reach stage 5 of SAE's driver autonomy. That would be dream achieved. Until then, concerns like these are what will guide humanity to innovate further in fields of artificial intelligence. This marks the end of our presentation. Thank you for your time, and I hope you learned something new. All questions, criticisms, and suggestions are welcome.